We are now looking at the exercise for the diodes. And so we look at exercise 9.11. It says, considering the battery charging circuit of this figure with Vm is 20 volts, means 20 volts, and let me use blue. Vm is 20 volts. This is the amplitude of the input voltage, and R equals to 10 ohm. VB is 14 volts. My bad. VB is 14 volts. And find the peak current assuming an ideal dial. So for an ideal dial, if you remember, for an ideal dial, and its VI curve will be just this. This is ideal. If it is on, then it consumes no voltage drop. So uh, let's look at this circuit diagram. This is a diode, and it's an ideal diode. And uh, so when there's a positive voltage, then it shows forward bias. However, this positive voltage need to overcome this positive 14 volt. So if it is on, so problem A for forward bias. So assume forward bias. So no, we do not assume. We just add a forward bias condition. A forward bias condition. So current will be Vm is 20 minus 14 because it need to overcome this 14 volt because this battery is positioned as positive terminals on the top. So if this is forward bias condition, this Vm need to overcome this 14 volts and then divided by 10, which is 0.6 ampere. So this is the peak current of the dial. Okay, this one should be simple. Second, find the percentage of each diode for which the diode is in the on state. So, uh, we look at this. We look at this. So the blue waveform here. This is input voltage, right? Input voltage, and if it's a if it's ideal diode, this red curve. So for this whole period of waveform, only here, diode is on. So it asks you to find the percentage of each cycle. So this is one cycle for which the diode is in the on state. Okay. So for because we assume it's an ideal diode, and then we need this input when the diode is on. We need Vn, we need a V in larger or equals to VB, right? Because if it's an ideal, if it shows if its curve is like this, if this is V, if this I, if it assumes a schedule voltage VR, then we need to have VB plus VR. Okay. But here there's no knee voltage. Assume this is no, so we have V, the input voltage needs to be larger or equals to VB for the dial design. So we have Vm psi omega t larger or uh, larger or equals to 14. Okay, and how about let's look at the margin. So this is at margin. So we have omega t. So Vm is 20 equals to arc sine 14 divided by 20. So we have which is 44.427 degree. Okay. And so suppose um okay. So so for example, the whole range. Let me use a different color. So another condition is 180 minus 44.427 degree, which is 135.573 degree. We will have for each cycle, we will have these 2 degrees, which satisfy this condition. And if we draw it, if we draw this on, if we draw the degree, so the whole circle, we assume it's 360 degree, and the first angle which satisfy here, the start here, it would be 44.427 degree. And here will be 135.573 degree. Let me double check. So if we have sine 0.7 and yeah, it should be. So because this sine function, the sine function, so suppose this is REIN, so this is sine. Both this is 44.427 degree, and this is 135.573 degree. Both of them has their sine there, so sine 44.427 degree equals to sine 135.573 degree. Okay, so we will have two angles, And because the angle for a cycle would be 360 degrees, so we can calculate the percentage. So the percentage, so when diode is on, so diode is on, or this is uh this is 300, the total period is 360 degrees. And when diode is on, the wave, it takes the how many angles? 1.135.573 degree minus 44.427 degree, which is which is 360, which is 25.32%. So the dial is on for this 25.32%. Okay. Uh, let's look at the next example. Okay. In this example, it says a power supply circuit is needed to deliver 0.1 ampere and 15 volts in average to a load. The AC source has a frequency of 60 hertz. And assuming that the current of figure 9.26 is to be used, the peak-to-peak ripple voltage is to be 0.4 volts. Instead of assuming an ideal diode allowed 0.7 volt for 4 diode drop. Okay, so right now we are focusing on this kind of assumption. So this is V, this is I. So the threshold voltage or knee voltage is 0.7 volts. Okay, and find a peak AC voltage Vm needed and the approximate value of the smoothing capacitor. So we need to find out the peak voltage, the amplitude of the input voltage, and the capacitance of the capacitor. So it gives us a hint to achieve an average low voltage of 15 volts with a ripple of 0.4 volts, designed for a peak low voltage of 15.2. Okay, so if you remember, we for this, because this is a dial, so suppose this is, let me remind you. So, so if this is T, this is V, if this is sine wave, suppose this is input, so this is input voltage, and then the low voltage will be, because we put the capacitor here, so if it's large enough, it will be like this. And because there's this ideal dial, it has 0.7 volt drop. And so we also need to consider that. And for this, it says ripple voltage will be 0.4 volts. And then so we have this approximately, this is period. Okay, so this is what we have. So, so this, so the red is low voltage. And um, we have we have a relationship. Uh, so the the capacitor, the charge, the which is preserved in the capacitor equals the the charge delivered by the capacitor. So the charge preserved in the capacitor will be the capacitance times VR. So this is VR. Okay. So this is the charge preserved in the capacitance. The charge preserved equals charge delivered. So it will be current times the time interval within a cycle. So we can have this is charge delivered, current times time. Okay, so we can estimate the capacitance as IL times T divided by VR, which is IL is 0.1, it is given, and the period will be the reciprocal of frequency. So it will be 1 over 60 divided by 0.4, which is 0.004167 Fahrenheit, which is equals 4167 mu Fahrenheit. And mu is 10 to the power of minus 6. So we got one answer. Okay. And second, what would be Vm? Okay, because so what would be Vm? What should be Vm? Because it says this because it says it delivers 0.1 ampere and 15 volts, and it has a parenthesis, it says average. So we know the average here should be in the middle. So this is 15 volts. And remember it's average. So the peak, this is the peak. We can approximate the peak by Vn uh, is we can approximate the peak by um, 15. This is 15. This is 15. We can approximate Vn by 15 plus 0.2. Okay, because it assume 15 is just in between this VR. So to estimate this peak, just 15 plus 0.2. And then because when it is under forward bias, we need to allow 0.7 volts voltage drop. So we need to add 0.7. Okay, because it will be deducted when the dial is on. So which means the VM the VM is 16.6 volts for this circuit. Okay, so we have two answers. Okay, uh, let's look at the next problem. Repeat exercise 9.12 using the circuit of figure 9.28 with the smoothing capacitor in parallel with the load RL. So we also using a capacitor here. We add a capacitor here. We add, you see. So sure, if both of them are grounded, that means they are connected. And this is C. And so let's redraw this figure again. So we have this B, C, okay. So for suppose this is input voltage and this is input voltage. And we have output voltage. So output voltage will have, let's consider voltage drop here. So if you remember, for each for each, so it also go back to here for forward and reverse bias. It always goes through two diode, which means the voltage drop will be 1.4. So before we put this before we put the capacitor, it will be like this, be like this, be like this. Before we put the capacitor, it will be like this. And after you put the capacitor, it will be like this. It will release the, so let me emphasize the curve. So the curve will be like, after we put the capacitor, it will be like this. Okay. And then we have VR. This is VR. And this is just half of the period. So this is T over 2. So if we want to estimate the value of capacitance, we have this C times VR equals IL times, but right now the discharge time becomes half of T, so times T over 2. So which means C equals IL times T divided by 2VR, which is 0.1 times 1 over 60 divided by 2 times 0.4, which is 2083.5 mu F. So we got the capacitance. You can memorize this. You can memorize this formula. Okay. And again, what is Vn? So the same thing. So average is 15. So we have 15. So Vn will be 15 plus VR over 2 because we need to estimate the peak. But we because right now it goes through two diodes for forward bias and reverse for for positive and negative voltage. So we have 0.7 times 2, which is 15 plus VR is 0.2, 0.4, VR 0.4 divided by 2 plus 0.7 times 2, which is 15 plus 1.2, 1.4, which is 16.6 volts. This is the peak of the input voltage. All right. And then we'll look at the next slides. Wave shaping circuits. So electric circuits used to transform one input waveform into another. And so this is a circuit. It can transform one input waveform to another, commonly used in television and radar transmitters and receivers. Let's introduce the first kind of wave shaping circuit, which is called Clipper circuit. So it is a specific type of diode-based wave shaping circuit that clips off unwanted portion of an input signal. So it is used to protect the electronic device because it can limits the upper bound. So here, if you look at this waveform, so the blue, the dot curve is the input voltage, and the solid line, it is the output voltage. So at B, it limits the output voltage between 6 volts and minus 9 volts. So we often use this kind of circuit to protect our device. So, and it consists of you can see there are two diodes in parallel, and these diodes they are in the opposite position. And then it also has a DC voltage source, 6 volts and 9 volts. It also, the polarities, they are also also opposite. And so if we have 15, if the input is 15 sine omega t, and it goes through a resistance. So let's focus on this branch. So what's the condition for diode A to turn on if we assume it's an ideal diode? If we just say ideal diode, it just means this is Vi, this is this. Okay, this is ideal diode. We just assume this knee voltage is 0. Okay, let's say knee voltage or threshold voltage is 0. Threshold voltage is 0. Okay, for A to turn on, it needs to larger than 6 volts. So for A to turn on, the voltage needs to larger than 6 volts, right? And for B to turn on, the voltage, so this is V in T, need to larger than 6 volts. For B to turn on, we need to V in T smaller than minus 9 volts. The smaller means its amplitude is larger than 9, but they are in the reverse direction. So we say V in T is smaller than minus 9 volts. So how about, let's go back to this. So how about when the diode turns on? When the diode turns on, suppose it consumes 0 voltage. So when diode turns on, is VO. So if we consume 0 voltage, then between these two terminals, the voltage is just 6 volts. Okay, when the dial turns on. So here it means this. At this segment, it means A, DA on and DB off. DA on, DB off. Okay, and how about let's look at this branch. So if VT is smaller than minus 9 volts, it means so it's here, this segment. It means DA off, DB on. So if a diode is off here, it means it is an open circuit. For example, if you look at here, if this DB on and DA off, then we don't need to look at, we just focus on this branch only. And if so, it's called, so for this kind of configuration, when the voltage larger than 6 volts, it eclipses at 6 volts. Okay, and when the voltage is smaller than minus 9 volts, it clips at minus 9. And what in between? So in between, in between, in between, it is DA off, DB off. So what in between is DA off, DB off. It means both of them are open circuit. So when you measure the voltage between these two terminals, it's equivalent because there's no current at this moment. There's no current consumed by the resistor. So at this moment, VO equals VIN. So for this, VO equals VIN because both A and B, they are off, they are open circuits. So um, so this DA on, DB off, and VO equals 6 volts. So here VO equals minus 9 volts. Okay, and so if we draw the relationship between the input voltage and output voltage, we can find out that if the input voltage is larger than 6 and the output voltage VO will be fixed at 6 volts. And if the input voltage is smaller than minus 9 and the output voltage will be fixed at minus 9. And what in between? Both dial is off, so the slope is 1. So at this moment, we have VI, V in T equals VOT. Or we have VOT equals V in T. So that's the answer. So we call this clipper circuit. We clips the top and bottom of the waveform. Okay, and if we look at the next page, this is some alternative of previous configuration. We can, because if you look at previous configuration here, it also, apart from the input voltage, it requires 2 voltage DC voltage source, and it makes the circuit more complex. So we can another way alternative is we are able to replace the DC source by the Zener dial. So so because you see the Zener dial, they are in the opposite polarity from the dial. So again, so the direction of the Zener dial is against the dial. It is in series with. So the Zener dial of this 8.4 volts, it is the polarity is against this dial. And we use the breakdown voltage. So 5.4 volts means breakdown voltage. It means for this branch to turn on, this input voltage need to overcome not only this 0.6 to 0.4 0.7 forward drop. So this ideal. So right now for this configuration, this diode it has a knee voltage and it approximates to 0.6 volts. And so for this one, for suppose this is A, for B, for delta A to be turned on, this input voltage needs to overcome this 5.4 volts Zener voltage. And in the opposite direction, for B to turn on, it needs to overcome the 8.4 volts Zener voltage of this dial. Okay. And so if we consider 0.6 volts threshold voltage of A and B, we can have the same result of we have with the previous example. So the output will be the output will limit the waveform between 6 volts and 9 volts. Okay, so this is an alternative of previous configuration. And another even simpler configuration and which has the same performance, it can be written as this. You use two Zener diodes and put them against with each other. So when the input is positive, so this diode it has a voltage drop of 0.6 volts, and to make this branch turns on, you need to overcome not 0.6 volts and also overcome 5.4 volts of the Zener dial, and then the VO will be 6 volts. Okay, for this branch to be turned on, so one dial is at its forward bias, and another dial is at its Zener region. Okay, reversely, if we think reversely, then this dial is on its forward bias, and this dial is on its Zener region. Okay, so both these alternatives they can generate the uh, same output voltage as the previous example. So this is you can Zener dial replacement. We use Zener dial to replace the DC batteries or DC source, and then we take advantage of their breakdown voltage. Okay, so this is the clipper, clipper circuit. We call this um, clipper circuit. Okay, um, I think we have an example here. Okay, let's look at the example. Okay, it already gives you the answer. So A, but I will explain the answer. Um, let's look at A. Sketch the transfer characteristics to scale for the circuit of figure 9.31a and B. Allow a 0.6 volt forward drop from the dial. B. Sketch the output waveform to scale if V in is 15 sine omega t. So, okay, let's split this. So if we, this is the answer for A, this is the answer for B. Okay, and so what can we do here? Uh, for A is easy. We look at this branch. So for this branch to be turned on, D1 needs to be at forward bias region. D2 needs to be at its Zener region. So you can also it can be also explained by you need to overcome 9.4 volts plus 0.6 volts for D1 and to make this branch to be on. And once this branch is on, then VO will be fixed at 9.6 plus 0.6, 9.4 plus 0.6, which is 10 volts. So V in need to be larger than the amplitude of the input voltage need to be larger than 10 for this to be turned, for this branch to be totally on. So we have this with D1 on, D2 at Zener region. Okay, and if the input voltage drops, so at this branch, it means V in equals VO. So I use different color. So for this segment, how about before we draw this segment, let's look at the condition that where which under which condition that we can turn on another branch. So in this branch, you notice they have three dial in series. It means to turn on this branch, uh, we have 0.6 times 3. You need to provide 0.6 times 3. It equals minus 1.8 volts. So we need to, so V in T need to smaller than 1.8 volts, which means it should be negative and its amplitude should be larger than 1.8 volts. So we can draw, so if this turns on, then VO will be equal to minus 1.8 volts. So we can have this. So this is this segment. And then, so for V in is, for V in is minus 1.8 volts, then VO will be always minus 1.8 volt. So for V in is smaller than minus 1.8 volts, the output voltage will be fixed at minus 1.8 volts. So this is D5, D4, D3 is on. Oh my bad. D1, oh D5, D3, 4, 5, D3, D4, D5, on. And between them is all the dials are off. Uh, between them they are all off. So here, delta of, and for that segment, we have VOT equals V in T. Okay, this is the characteristic diagram between V in and V out. And it also asks us to uh, sketch the output waveform if V in T equals 15 sine omega T. So just the here. So this is the dot line is the input voltage. The solid line is output. So the output voltage is at uh, clipped at 10 and minus 1.8. Okay, this one should be relatively easy. Okay, uh, let's look at this plot B. So plot B, okay, it has only one branch and it has a dial D6. Oh, it has two center dial. They are in the opposite polarity, but what's the difference is it has what different from before is it has a 1k ohm resistors here because previously we just have 1k ohm there, but this 1k ohm resistor it will affect VO. So we need to consider that. Uh, how about let's consider uh, let's consider positive okay we say this positive 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 voltage. So first case positive voltage. So this is B. I'm going to use blue color. Input voltage. Well, it's a positive V in. So for current I. And so if it's positive and assume the dial is either on or oh, assume the branch is on. The branch is turned on. We have I equals V in minus 5 because it need to overcome this threshold voltage of this dial and the Zener voltage of the second dial. And it will be 4.4 plus, yeah, let me say 4.4 plus 0.6 and divided by 2K, right? And which is V in minus 5 divided by 2K. Okay, so when the branch is on, so, and then at this moment, what is VO? VO, how about, let's say, this is on, oh no, I said this is on, D6 on, and D7 is in Zener region. This is first part, and then we can calculate we want to under this condition we want to estimate VO. So under this condition, VO is VO will be 5 because it will take this is 5 volts in total, and then VO is 5 plus the current I times 1K, right? Plus I times 1K ohm. Because because when this branch is on, then the voltage here of these two Zener diodes, it is fixed at 5 volts. But the voltage across these resistors, it it depends on its current, right? So we have 5 plus IR, which is the voltage drop between these resistor. So we can have 5 plus, this is V in minus 5 divided by 2K times 1K, which is 0.5 V in plus 2.5. Well, we got the equation here, which is VO equals 0.5 V in plus 2.5. It means D6 is on and D7 is at its Zener region. So it happens to be this segment. Because when input voltage, the amplitude, when the input voltage, the amplitude of the input voltage is larger than 5, and it falls into this region, or I can say V in T is larger than 5 volts. It falls into this region. Okay, and for this region, we can estimate an equation for the input voltage and output voltage. I hope you can understand. Okay. And you can plug in a number, 5. If we put V in equals 5, then the VO will be 5. If we put V in is 15, and VO will be 10. Okay. Let's look at the when the when the V in is smaller than minus 5. So okay, the second condition, V in T is smaller than minus 5 volts. What would happen? Same thing. So at this moment, all the current flows reversely, and we have I equals V in T. Please remember, right now V in should be a negative value, and you need to overcome this 0.7 volts, part 0.6, and also overcome this 44 volts Zener voltage. So it is plus 5 because V in is a negative value, and you need to overcome these 5 volts, including the threshold voltage of D7 and the Zener voltage of D6, and divided by 2K. This is the I. And when it turns on, VO, so we say, so here, so this is, at this moment is D7 on, D6 Zener region. Okay. And we need to estimate, since we have I, we need to estimate VO. So VO should be, remember, this is plus, negative. So this 5 volts drop is in the opposite polarity with VO, so it's minus 5. Minus 5. And and the polarity here, it should be positive, negative. So it's also in the opposite direction of VO. It's in the opposite direction of VO. So it should be minus 5 and minus. This is V in plus 5. Am I correct? VM minus 5. How about let's say it here. Let's write it here. We have VO equals minus 5. And we have this current. We have this, the current is minus, let's see, V plus, how about V in plus 5 divided by 2, that's 1K. Let me check this first. Plus, this is 0.5 V in, and plus 2.5 is 0.5 V in, minus 2.5. So we had another equation here, which is here. If this is minus 5, this is minus 5, this is minus 5. Okay. If it is minus 15, it is minus 10. This is minus 15, 2.5 times V in is minus 15, and then minus 2.5, it is minus 10. Okay, this equation is correct. Okay, okay, and um, so it follows plus 5 minus. So if it is minus, okay, we assume it is minus, but in fact it's plus. Okay, so we have the equation here. This is VO equals 0.5 VN plus 2.5, and we have this. This is VO equals 0.5 V in minus 2.5. And what in between is both of them are off. So here it's VO equals V in. All right. So this is minus 5 plus. Okay, we always assume this I V in plus 5 divided by 2K. Okay, so this is plus negative. Okay, we just assume this I is flows reversely. Okay, we just assume this still I, V in plus 5, V in plus 5. Okay. Mm. Yeah, because the reason why this is still plus, I'm not sure until now if you can follow me or not, but the reason why it is still plus is the polarity here because the negative current is inherent within this equation. So we just use -5 because we have this 5 volts and they are in the opposite polarity with VO. And then here we plus V in plus 5 divided by 2K because for here we still assume current flowing this way, but in reality, in fact, it is a negative. So, but we keep this times the 1K ohm resistance. It is the voltage consumed by this part. So we have this. We come up with this characteristic equation, characteristic diagram between V in and VO. So this is quite special. And so you can notice it is not clamped anymore because it has a resistance here. A resistance, once there's a current flow through this resistance, then its voltage will keep increasing. And if it's a negative voltage, also its negative voltage keep increasing. So it's always symmetric. So you can use this symmetricity to double check your answer. And for the middle segment, it means VO equals VI. So the slope is 1. Okay, so this is uh, this is what you can pay attention to. And if we look at, so to sketch this input 15 sine omega t, supposedly if without the resistance, it will be like this, right? It will be clipped. It will be clipped. But with the resistance, it won't. It has a voltage, but because of this slope, the output voltage will be smaller than the input voltage because it divided by times 0.5 plus 2.5. So to find out this point, and then you can use this equation. So at this point, VO equals 0.5 times 15 at the peak plus 2.5. It should be 10 volts. So we can approximate this curve. Same thing here by using another equation. So by using another equation, we have VO equals 0.5 times minus 15 minus 2.5, which is 0.5 times minus 15 minus 2.5, which is minus 10. So at this point, it is minus 10. So you can approximate this curve. So remember, if you notice there's a resistance, also put a resistance at the output, and this won't be, the output waveform won't be clipped. It will increase, but its amplitude will be smaller than the input voltage. Okay, so we finish today's lecture.